as this is an evening talk, this gives me an opportunity not just to dive into science, but also to tell the story, the success story of this field from a subjective perspective. And I think that is also interesting for people who are in the middle of making a career. A lot of this was not planned. And my talk about the wonderful world of pedestrians, we'll see, is also a plea for the freedom of science. Because a lot of that would not have happened if everything in science would be planned. The title is somewhat inspired by this article over here, The Wonderful World of Active Many-Particle Systems. In fact, however, I should have perhaps chosen this title over here, The Adventurous World of Pedestrians, an event-driven approach. Because it was all a lot more exciting than I ever expected. Not just the science of it, also everything around it. And just to avoid any misunderstandings, I'd like to say, no, my work did not receive the IG Nobel Prize. Okay? Now, everything started in Göttingen, where I studied. And Göttingen has teared down, in the meantime, the Physics Institute where I did my diploma thesis, so I cannot show you a picture. But I show you a picture of the center of the city, and I call it the navel. And really, they understand it as the navel of the universe, which was very surprising, a little bit irritating to me. Perhaps, if you wish, it could apply to early quantum physics, because there were really big shots over there at that time. I was doing my diploma with Manfred Schroeder. I'm not sure you know him. He started being a professor in acoustics and physics of waves. And then he eventually got interested in all sorts of things, also strange things, such as strange attractors and fractals, chaos, and including also self-organization. And this is also which allowed me to make my diploma with him on a very unusual subject. I had always solved the questions that he had raised in his lectures, so he trusted that I was able to work on a totally off-road subject, and that was on physical modeling of the dynamic behavior of pedestrians. It was a thesis that also included some photos, quite unusual, I think, at that time. And you can see over here some photos that inspired me to take this road, because somehow it suggests that there could be some fluid dynamics in play. And I've also been taking pictures in all sorts of situations. So I've been doing field work, you could say, empirical studies. And does anybody recognize something interesting in those really old pictures? No? And you share this actually with most of the people in the world, because until I published about it, basically there was no mentioning of the fact that there was a lane formation phenomenon in pedestrian crowds, and that people tended to walk on the right-hand side, at least in the middle of Europe. Things are different in Japan, where people walk on the left-hand side, but there's also lane formation in Japan. All right, so these things were very inspiring to me, and this is basically the table of content of my diploma thesis, as you can see over here. So it contained parts on individual behavior of pedestrians and a mathematical modeling of this. It contained parts on a gas kinetic and also fluid dynamic description. So I set up gas kinetic equations that were considering that there was no conservation of momentum. So there are additional terms which complicate the equations, and then I derived macroscopic fluid dynamic equations from that. And not only this, I also did computer simulations, which was very difficult at that time because computers were not very powerful. And so basically I had, if I recall well, an Intel 386 or 286, one of those. And it literally didn't allow me to simulate 500 pedestrians, even modeled as simple as particles. And so I had to come up with a trick. And what I did is I was using the memory of the computer screen. And so the display was also storing basically the data of the simulation. So I did an early GPU computing without even knowing that it would be called GPU computing. So anyway, so I found a solution. And at that time, physicists found the subject of modeling pedestrians funny, to tell the least. They did not really know what to think about it, to be honest. And now you may wonder, how did I get interested in the subject at all? And I said, I'm taking an event-driven approach. In fact, this has to do with the 17th of November, 1989. What happened on that day? Connie Wessmann died. I didn't know Connie Wessmann. But what happened, basically, there were conflicts between different groups in Göttingen, like right-wing and left-wing people, and sometimes the police was interfering, and in this case, it ended with the death of that person. And the police had said a few, perhaps, stupid things over the walkie-talkies, and so the entire public was outraged about what has happened. And there was a huge demonstration where people have been demonstrating for the first time of their life. And it was pretty shocking for people who were at the demonstration for the first time, because also they had those kind of water carriages and weapons, in a sense, to go against normal people. And it all ended, as you can imagine, in a big, big, big mess. So things were even worse afterwards. And people were totally shocked and didn't know what to think and what to do. And so there were public debates about it, in particular in this theater in the city of Göttingen. And they were discussing about violence and counter-violence and what was allowed to be done or what should be done. But basically, I came to the conclusion that everyone was using the same words for different things. And therefore, they couldn't come to a constructive conclusion. So I decided what was needed is a scientific approach where you first define the meaning of the words, and then you work with those definitions in order to come up with a solution. So this was basically the day where I decided I would do social physics. And there was no such name like social physics at that time. But I wanted to do social science from a physicist's perspective. And I was starting to look for literature and subjects, which was also quite difficult at that time because Google did not just bring up the work that you were looking for. You had to go to the library and fill in forms with typewriters and all these kind of things. And sometimes you had to wait for weeks to get a book from New York or Washington, D.C. or whatever. The three subjects I chose as possible subjects for my diploma was arms race, group dynamics, and pedestrian modeling. And I came to the conclusion that pedestrian modeling fit the bill best because it was closest potentially to physics. And so I wrote this diploma thesis, and then I wanted to move on in science, and I was looking for a PhD position. I was reaching out also to Manfred Eigen. There was also an opportunity to work on the theory of evolution. I've done also some work related to social systems at that time, but finally I decided to go to Stuttgart to do my PhD with Wolfgang Weidlich, because that was just closer to my heart. I was more interested in really learning about how social systems work. And he was basically one of two, perhaps, physicists in the world who were at that time working on social system. That was the beginning of the 70s. He started with this. I came, I think, around 1990 to Stuttgart. And so this is the building where I was working in. And the first thing I did was basically write up the results of my diploma thesis without being asked by anybody. I just wanted this to share this with the world. And at that time, I did not know anything about impact factors, actually. I just had to find a journal that was suited, and that was behavioral science. And you can see some of the equations over here. So at that time, I already introduced kind of agent-based ideas and the social force model idea and some other stuff as well, for those who don't know the paper. But the problem at the time was basically that most people in science thought it's neither physics nor sociology. So basically, it was not clear where to publish that stuff. And I was submitting this paper that Torsten already showed to you, the fluid dynamic model for the movement of pedestrians, to a fluid dynamic journal, or even two, and they said, this is not physics. And so it eventually ended up in complex systems. And also, I think not a high impact factor, but both papers surprisingly have quite some citations collected in the meantime. And that is really a big surprise to me. Now, there's some interesting scientific puzzles, I believe, related to pedestrians. For example, how important really is psychology or sociology to understand what's going on in a crowd? Then how does self-organization, how do collective patterns of motion come about, like the lane formation I mentioned? Why do efficient patterns of motion break down? Do we need to assume a planning and optimization of trajectories? This is, for example, what computer scientists often assumed, and roboticists do. And there were some modeling approaches for pedestrians at that time, microscopic ones, mesoscopic ones, and macroscopic ones. Last ones, I was one of the main contributors. But I also introduced a microscopic model, the social force model, that really made a tour around the world, you could say. So this was obviously inspired by physics. The idea was that we could describe the behavior of pedestrians like by an equation of motion. That's probably not so controversial. But then the question is, how would the speed change in time? We would need an acceleration equation. The assumption that I made was basically that we could approximate that by a superposition of forces. And it would be a driving force that describes the adaptation of the actual velocity of pedestrian alpha to a desired velocity, desired direction of motion, and it takes a little time to accelerate. And then there would be interaction forces, mostly repulsive ones, with other pedestrians, and there would also be repulsive interactions with walls. And in many cases, we add also a fluctuating force because people don't behave in a deterministic way. One of the papers on the social force model was published together with Peter Moller back in 1995, and I cut out the original equation from the paper over here, and we simulated a multi-particle system, driven particles, mimicking pedestrians, and we found some interesting phenomena, collective patterns of motion, such as oscillatory flows at bottlenecks. You can see it over here. And the question is, how does that happen? There's no traffic light here. There's no police. Nobody's telling people what to do. So basically, people come in and the pressure builds up, and it's kind of the built up and relief of pressure that creates the oscillatory flows. With the same model, we could also simulate the length motion. Also, that's an original figure. And you can see it over here. Those are really some old simulations, I believe, from that time. And it's pretty clear that there's this separation of different walking directions. And many people find that interesting, not only in physics, but also in biology and many other fields. This paper, amazingly enough, made it to be a milestone paper of Physical Review E. Actually, it's now my most cited paper. I'm totally astonished. It's also the most cited milestone paper, by the way. Now, why was it so influential? Well, because people in robotics, for example, were inspired by the social force model to teach robots navigate in a crowd. This is just one thing. Then similar phenomena were found actually in other fields of physics, like colloids, and of course, granular material. Right? And so it's no surprise from today's perspective that eventually those fields found together, and there was a series of conferences which is still alive on traffic and granular flow. And this gives me also an opportunity to mention a couple of colleagues and friends who were really important for the creation of this field. This included Hans Hermann, Michael Schreckenberg, Dietrich Wolf, who's sitting with us, Andreas Schadschneider, of course, Thorsten Pöschl, Reinhard Kühne, and also perhaps I should mention Armin Seyfried as well. So there are many people actually who brought up that field. So basically, you're now seeing the emergence of something that was not even a science that had a name into something that became a field with a community around it. And that was very important, of course, for success. Eventually, I was employed in the collaborative research project SFP 230, which was called Natural Constructions. And this was actually brought up by two very inspiring people, Fry Otto, who also basically invented the construction for the Olympic area in Munich. You all know it, of course. It's really totally amazing and unique. And Klaus Humpert, both architects. And they were interested in what was happening in nature and what we can learn from it, including those trails that were forming in emergent ways, unplanned ways. And at this time also there was a conference that Werner Ebeling and Wolfgang Weidlich organized together. So that brought basically West Germany with East Germany together. And this is also where I met Frank Schweitzer. Frank Schweitzer was also involved eventually in the SFP 230, but in Berlin. And we eventually published a paper in Nature. So basically the architects had inspired me that it was the formation of trails, but they hadn't any equations for that or any model at all. And we came up with a model, and Frank always told me, you know, you should publish in Nature or Science. And that was kind of the time when I learned about impact factors. You know, my professor did not care at that time. You know, you cannot imagine there was a time without impact factors, basically. You know, people not caring enough. And so, okay, if Frank says we should publish in Nature, let's try. And actually, it works out. So I really have to say thank you to Frank, because otherwise we'd never submitted to Nature. And eventually we published together, so you can see over here a paper that was about transformation also among ants. And eventually that qualified me for another Nature paper about ants under crowded conditions, which are actually doing a very good job to avoid traffic jams. And this made me get interested in swarm intelligence. So later on, we worked about collective intelligence, as some people may know. But altogether, one could say that this kind of research brought physics on new paths. So the general physics community got interested in the subject at the time. And eventually, I was invited to Budapest by Tamas Witczek. Some people of you certainly know. He was interested at that time in flocking of birds. But at the time when I started working with him, he got interested also in the question of crowd disasters. And here there are some scientific puzzles again. So why do crowd disasters happen, even if nobody wants to harm anybody else? Are crowd disasters a result of people who panic, or are there any other reasons? Are they a result, perhaps, of physical interactions? At the time we started, everyone saw it's a psychological phenomenon. After we published, people eventually learned it's mostly a physical phenomenon. First work along this line was about freezing by heating. We were basically introducing noise into this self-driven many-particle system that would normally create lanes. But if there's too much noise, basically what happens is that those lanes of uniform walking direction break down, and we get two blocks of people and somehow a non-equilibrium crystal, you could say. That's why we call it freezing by heating. That was also discussed in Nature by Gene Stanley. But the really big paper about panic was this one. I think that came out in 2000 or 2001. And it had a number of things that we were looking at. One was spreading behavior in rooms of reduced visibility. So in case you couldn't see the exit, you would have either to find a way out yourself, or you would follow others. And it turns out that too much herding can be very counterproductive, but that's actually what often happens in situations of disaster. What found more interesting, however, were those simulations over here. So basically, simulations of the evacuation of a room. And one of the scenarios that was not even in the paper, but on the supplementary webpage, this one over here with a pillar in front of the exit, I think that got actually most attention, surprisingly enough. So here you can see one of the simulations we did at the time. You can see that if people push too hard, then basically a clogging effect obstructs leaving of the room. And so basically, the faster they want to get out, the slower they actually manage to evacuate the room. So there's a faster, slower effect to the room. And this seemed to inspire a lot of people. So this Nature paper really made pedestrian research a global phenomenon, I would say. And it also had feedback effects, again, to the granular media community. So people were interested in, could we avoid silo clogging by putting an obstacle in front of the outlet? And then people were looking into panicking ants, panicking mice, and even into sheep. It's really amazing, something that I never had in mind to trigger, but apparently that paper made people think about all sorts of things. And there's even a nice complexity explorable that has been created by Dirk Helbing. So in case you want to play yourself with obstacles and pedestrian flows, I recommend you to do that. Around that time, we established the Physics of Social Economic Systems Working Group. It turned out to be a difficult job at that time. Now it's a division of the German Physical Society. I think that was really instrumental, a great success. I tried that together with Frank Schweitzer back in 2001. And it was really a difficult discussion, I should say. So, first of all, there was this book by Gene Stanley on economic physics, and it was highly controversial, also because there was really a legal case with Benoit Mandelbrot. Because Gene claimed on the back of the book that he was the first to use scaling laws for economic systems, and Mandelbrot said, no, I was the first. So basically, the book could not be sold. So economic physics was highly controversial, not only for this reason, but also many people were asking, can we really transfer physics to economics? And the economists were skeptical too. So basically, Peter Henge really had this book in his hand and said, we don't want this. He knew exactly what his colleagues were thinking and feeling about social and economic physics. So, you know, he was really attacking this book to show that he was on their side. But then he said, but I think we should give them a chance. And this is how it started. And in fact, I really think it was a good idea. There were then focus issue of the Physik journal, and a few years later in Bild der Wissenschaft, Formen für alles, kind of more than 10 pages about social and economic physics and what it could do. Yeah, so a lot of interesting things had happened. And then I got a professorship in Dresden. I think that had to do with my habilitation, partly. I've written this book about traffic dynamics. I was not allowed to write it in English at that time, just to inform you. My professor told me, you should not be kind of violating rules two times. You know, on the one hand, doing physics of non-physics systems, and on the other hand, writing your thesis in English while the regulation required to do it in German at that time. You know, that changed, obviously. Okay, so that's in German. And this was the faculty in Dresden at that time. And I've been working there for about 7 years, from about 2000 to 2007. I wrote this review article, which also has chapters about pedestrians, a little bit on granular materials too, very little, but anyway. And then we got interested in doing experiments, and in fact, as you can see over here, evacuation is a dangerous thing, so people may easily fall. And then the question was really, what would an obstacle change? And it makes actually the outflow more fluid. We were interested in all sorts of settings, bottlenecks of all kinds, unidirectional, bidirectional flows, crossings, and so on. And here is a famous drawing from Japan. I think it was created by observation of that crossing that I showed really at the very beginning. And this is quite surprising. If you want to cross a stream of pedestrians, you know, it's sometimes so dense, it's very hard to pass, like if it was a wall. If there are two streams of pedestrians, then suddenly everything is very easy. You just walk and you never stop. And how does that work? Well, again, through pattern formation. Stripe formation effect. And those stripes are moving forward, and the pedestrians at the same time are moving sideways in the stripes, and this is how we can basically cross the other stream. So just to show you a simulation, if you can't believe it, but that's actually happening. So it's in a sense a generalization of the lane formation phenomenon for crossing flows. Okay. So basically, is this useful or is this just funny? And in fact, it's useful. One can basically improve flows of pedestrians at intersections by subdividing an intersection of 4 crossing flows into 4 intersections of 2 crossing flows, which will create a more orderly behavior and more efficient flows. In fact, if you look at the standard elements of pedestrian facilities, like corridors, bottlenecks, and crossings, then all of them are wrongly designed. All of them can be improved. You know, after kind of so many 100 years of architecture, it's kind of surprising. I mean, for the bottlenecks, it's really clear, everyone understands that cutting away the corners will improve the flow, right? But it's nevertheless interesting that there is a less is more effect. Taking away space improves the outcome if you do it right. So we started to get inspired by this, and we're asking, could we put obstacles into the way, and would that, if well done, improve the flow, right? And in fact, the using corridor that separates the opposite walking directions, as we have that over here, for example, and it helps to separate the flow directions. And I already mentioned the intersection, okay? And we've done a lot more on this, but let me move on. So eventually those models were really getting interesting also for evacuation simulations. And there are companies that are using them professionally, commercially, to check for the safety of buildings and ships and football stadiums and large mass events and so on. And those simulations, I mean, the visualization still looks a bit funny here. These are not the most recent videos. I'm showing you of the time when they were first created. And so basically, now this is an industry, in a sense. What started as a funny subject became really applied all over the world. And people were reading about it in the newspapers. And one day, basically, somebody from Infineon Technologies in Dresden came and talked to me and said, could you help us to improve our chip production? I said, well, I have to see, let's go there and look at what's going on there. And so basically, this is the situation that they had. They had a production system for vapors, silicon vapors, and they wanted to reach this through, which was promised to run the screen, but that's all they managed to get. And so they were making a lot of measurements to find better configurations, and of course, you could not measure for all parameter combinations. There were just too many, so they were extrapolating between measurements, and the extrapolation really didn't work. That was a highly complex problem, and this was actually the machine. Just to give you an idea, there is this handler that is moving around the vapors and putting them into different kind of chemical bases. Then they have to be cleaned in order, and then they go into the next chemical, and so on. And you have several sets of vapors that basically have to be handled in parallel. And this is where the problem starts, because sometimes several sets of vapors want to be handled at the same time, and then one of them has to wait, and that can cause delays. And if those vapors stay too long in the chemical, you can throw away the vapors because it's not good quality anymore. And what we said at that time was, you should perhaps try to apply this slower is faster effect. So we slowed down the treatment times paradoxically. But that reduced those conflicts for the use of the handler. And so through this trick, basically, we could really increase the throughput by more than 30%, which is worth several millions, basically. Not that I did get these millions, but for Infineon, that was really useful. Eventually, I was moving over to Zurich. So we started in the so-called UNO building, then a little castle. And now our office looks like this, kind of an open co-creation space. And around the time, we became hold of trajectory data. I should tell you that at the time when I did my diploma, of course, I was thinking of scattering theory to measure the interaction forces and potential among the pedestrians. But I would never imagine that technology would become available that we would have the data to basically research it. So technology really progressed so dramatically that eventually we could measure trajectories, thousands of them, and that allowed basically to do calibration of those models. Before it was just theoretical models, assuming certain kind of parameters. Now we could calibrate. Not only this, we could even go a step further and make experiments with people and measure the trajectories and interactions between people. And it would give us a lot of data. So much data that it was actually possible to determine the empirical force field. And that was really very nice. On the other hand, we got interested to study crowd disasters further. And here, we also got access to video material of a crowd disaster that has happened. And that was actually at the Jamra Bridge, Mina, close to Mecca, Saudi Arabia. This is the old Jamra Bridge. It's here where a stoning the devil ritual is performed. But while crowd disasters had often happened around those pillars in the past, back in 2008, it happened just over there, around the entrance area. It was kind of surprising for many, but the reason was that it was basically a confluence of different flows that created effectively a bottleneck. And if you looked at the video recordings, basically you saw nothing. Until I suggested my PhD student at that time to accelerate the movies by a factor of 10, 20, 50, 100. And suddenly we were totally shocked to see that there were patterns. So there was a transition from smooth kind of laminar flow to stop and go waves. And then those stop and go waves continued for about 30 minutes. And then there was another transition to a further collective behavior, which we called crowd turbulence, where people were pushed around into all sorts of directions because the density was so high that they were really squeezed in between other people, and forces were transmitted from one body to the other, and sometimes people were pushed around for many meters. And that is a condition where basically there's a danger that people would fall, and a hole would be created in the crowd, and then other people would fall on top, and that would create a terrible crowd disaster, unfortunately. So it turned out that physics was really the reason for crowd disasters, perhaps not for all of them, but for many. And it's now an established theory, and also it has really had an impact on the organization of the Hajj, which had been, everything had been reorganized. There's also a new Jamra Bridge now. Now there's unidirectional flows, and there's an avoidance of crossing flows. And in the year they did not strictly follow those rules, another crowd disaster happened. So it's really instrumental to avoid crossing flows. Then back in 2010, another power disaster happened. That was in Duisburg during the Love Parade. Now, it should have been a happy festival. Instead, I think 21 people or so died, hundreds were injured. The chancellor and the president of Germany at that time said, we really need to figure out what has happened over here. So in all little detail. And so I thought, as a crowd researcher, it's my responsibility to look into this. Now, the situation was quite different at that time. In Saudi Arabia, there was not much publicly accessible material about the cloud disaster. Very differently so in Duisburg. There were a lot of videos uploaded to YouTube, hundreds of them, in fact, and I've been viewing a lot of them. I'm collecting this material, I've been evaluating it, putting it into a timeline, considering locations and all these kind of things. And the most difficult part of this paper was basically to avoid not seeing the forest for the trees effect. I mean, really helping people see what matters. This was actually the area where the festival happened. Over here, everyone had to come through a tunnel. At some time, people were starting to come back. This created an overloaded ramp. Police cordons were formed. That was not very helpful, as it turned out. And in the end, there was a crowd disaster as a result of what I call a systemic failure, where actually many mistakes added up and altogether created that terrible outcome. So in a sense, many different people and institutions had some role in this crowd disaster. It was not one person or one institution. And also what I found out is a lot of people could have stopped it, even pretty late. And I worked out how that could have been done and what were alternative scenarios to organize this. And you can imagine this had quite some impact on the legal procedures also. In the beginning, actually, the court wanted to close down the case. That was, of course, very shocking for the families of the victims. And after this kind of scientific results were available, that really couldn't be done. And so they had to reopen the case, and they were looking into this, and there were investigators, and I think in the meantime, thousands of pages of investigation of this case. It took 8 years basically to complete the evaluation. And then the result by this colleague was that basically the crowd disaster could have been prevented and confirmed basically what I said before in 2012. And in the end, unfortunately, the court case was nevertheless stopped. And they used the COVID pandemic as an excuse. And I did that on 7th of April, 2020, just a few days before this paper was published, which basically reconfirmed with a lot more scientific evidence that the crowd disaster could have been prevented. Here we were using not only computer simulation, but also virtual reality approaches, so quite advanced approaches. We were looking into different kinds of scenarios, how to organize the festival, and what the implications were and the performance in these scenarios. And it turned out that the police cordons actually had unfavorable effects. But the police was never a suspect in the case, you know, even though already back in 2010, there were some experts who were basically pointing at a problem over there. Again, they were not the only ones involved, but they certainly had a role in this. Okay, so basically, how can we save lives? Now we've learned really, pedestrian research is also about life and death and how we can avoid crowd disasters. And so basically now with information systems, we can give people information about the places which are safe and the places which are crowded, and the places they should be avoiding, or would give them basically some hints about alternative routes if there's some overcrowding in some place. And this is the kind of apps that were developed at the time. And that was basically just one step ahead of a lot bigger project that was called Future ICT. Back in 2010, the European Commission wanted to have two 1 billion euro research projects related to digital technology. They wanted to get on the world map of digital technology. And so I've been pushed at that time to apply for this. And we had this idea to create something like a knowledge accelerator or innovation accelerator. So a little bit inspired by CERN. At the same time, we were also inspired, of course, by the Apollo mission. And we said that basically we know more about the stars and the universe than about what is happening on this planet. And there's so many problems. So we need to change this. We need to learn what's going on Earth and why. And we were proposing 3 platforms: a planetary nervous system, a living Earth simulator, and a global participatory platform. In detail, of course, everything was a lot more complicated, and we were planning exploratories for financial systems, health and epidemics, crime and conflict, and so on, sustainability, energy, environment. And we got actually more than 30 countries on board, not only in Europe, but also the Americas, Singapore, Australia, Israel, many other countries. So basically, we really had a global aspiration. And we got many institutions on board. I think 2,000 scientists, about 150 academic institutions, also the research organizations, business partners of all kinds. And Future ICT was really the most popular project at that time, according to web statistics. And then in the very last moment, it was killed, basically. And everyone was stunned. And it turned out that actually there were a lot of countries that were interested in that kind of idea. In the United States, in Japan, in Russia, and in China. And so basically, to make the story short, they wanted to have such a thing for themselves. But they did not take the privacy, respecting, democratic, ethical, participatory route that we were proposing. Instead, the idea was basically to create a huge machine, a prediction machine that would basically know what was going on in the world and would take it into the future. So basically, just assume we take the entire internet and all its data and all the Internet of Things data and put it into a big supercomputer, a learning machine, to create something like a super intelligent system to save the world and humanity. All right, but the question was, can the world actually be saved with a war room approach? No. Can a centralized machine, in a sense, no matter how intelligent, could it really save planet Earth and humanity? Or would it be an even bigger problem and danger? So would our civilization perhaps be replaced by a militarization? Would military thinking take over? And in order to judge really how well that would ever work, let us look in a much smaller problem that we studied in detail, which is traffic light control. And we wanted to have basically a traffic light control that works for complex street networks, can handle with traffic disruptions, and also particular events like Olympic Games, pop concerts, and so on and so on. And this was inspired again by the pedestrians. Because we had seen that there were oscillatory flows at bottlenecks as if there was a traffic light. So we had the idea, couldn't we use that pressure principle that created those oscillations to define a traffic light control? Couldn't we have the traffic flows control the traffic lights bottom up rather than the traffic lights controlling the traffic flows top down, as it was done before? And as you can see over here, in fact, we came up with approach, a physics-inspired approach, which creates self-organized green waves. Here we assume just local interactions, like of the scale of neighboring intersections. But we introduce interactions in such a way that those traffic flows would coordinate. And the question is, how efficient is that? How well does that compare actually with the traffic center control approach that we have today? And in order to basically figure it out, we talked to the authority in Dresden at the time. They said, we are happy with our traffic light control. We just bought a new state-of-the-art system, cost a few millions. It even produces green waves, adaptive green waves on top. And the only thing we're not happy with is what happens in the center, because here we would like to prioritize public transport. This is the area we're talking about. And those are the tram and bus lines that cut through, and that really mess up the system, basically. If you would prioritize those trams and buses, then it would trigger congestion. It would become a monster traffic jam very quickly. Okay? They said, if you think you're smart, then find a solution for this. And in fact, we were working with the data. We were coming up with a system that would not impose green waves as on the top, but we would have self-organized green waves that are a lot more irregular, but that's because those adapt to the real traffic flows locally, to the real needs and to the opportunities of gaps in the flow. And it turned out, in fact, it allowed to prioritize public transport without harming individualized motorized traffic, and was also good for pedestrian cyclists, and by the way, the environment too. That was kind of surprising. So much surprising that some people couldn't believe it. So a chaotic traffic light control should be able to improve traffic flows. How is that possible? And then I changed to Zurich, as you know, and basically we were talking also to the traffic authority over there. It took 2 or 3 years. Then all the critical questions they had were answered to their satisfaction, and a newspaper article came out like the revolutionary idea of the professor, the traffic controls traffic lights. Perhaps that was too revolutionary, actually, because they were afraid that it would work too well. Plus, we were asked to come up with a new paradigm when we were creating the Future ICT project. And we said, basically, the world's organization is going to change from top down to bottom up. And so basically, Future ICT was turning the world around. And not everyone liked that. Actually, if you look at the poster, just by coincidence, did you notice? Bottom part, people are top down. In fact, it was so revolutionary that the talk I gave when I got actually an award for this, this movie has magically disappeared. But nevertheless, the PhD student of that time, Stefan Lemmer, stayed on, and he persisted, and he actually then implemented later on such a traffic light control in Switzerland, Lucerne, just half an hour from Zurich. And of course, they didn't believe it first, so they were measuring before, they were measuring after, and it was independently evaluated by an ETH institute. They didn't even tell me about it. And it was all totally, shockingly convincing. So basically, this traffic light managed to offer more green for all the different modes of transport. It's kind of hard to imagine, but basically, it's just using green time more efficiently. And you can see it over here, the red stuff on top, there basically largely disappears, and that means traffic jams are largely reduced. And now you could ask, is actually machine learning improving over this? And we've been looking into this. It was just a PhD defense on this, and it turns out actually, no, machine learning is not doing that better. So in conclusion, we cannot control everything top down, not even a city. How would you want to really control the entire world in a top-down way by a huge, monstrous machine? And we've warned of this actually back in 2013 in a Nature paper about globally networked risks and how to respond, where we basically also pointed out this, that in a world that gets ever more connected, the properties of the components matter less and less. What matters more and more is the network, the interactions between the components. And that would cause not only the intended effects, but side effects, feedback effects, and cascading effects. And paradoxically, in a sense, this would become ever more important. And even though we would have better technology than ever and more data than ever in the entire history of humanity, we would lose control over the system that would become ever more complex. However, complexity grows faster than data even. And this is why you use top-down control, which means you would need to come up with a new control approach, which would be bottom-up, to avoid these kind of cascading effects that we would otherwise see, like in the financial crisis. And so basically, very recently, a paper came out about the role of complexity for digital twins of cities in this case. And the main point basically is that digital twins are lacking complexity science. Complex systems need to be designed to support self-organization. Smart cities need to be designed to allow for self-organization. Smart nations too. Kind of one day after that, Geoff Hinton basically started his world tour warning the world of existential threats from AI. Of course, can be total coincidence. Geoff Hinton is really known as the godfather of AI, and actually for a reason, He has more H-index of more than 200 and more than 100,000 citations per year. I mean, this shows how small everyone really is. And he had to tour around the world and say, I was wrong. Do you know what that means? So basically, I was very happy when Giorgio Parisi got the Nobel Prize back in 2021, because he pointed the world to swarm intelligence, to collective intelligence, to self-organizing systems, and how important they really were. Because that is the paradigm on the right. Sorry, that went wrong. There was another Nobel Prize by that Richard Thaler actually received. And you see a book that he published about misbehaving. And over there, the words for looks very different. It's not a self-organized system, it's more like a crystal. It's a military order. And you know, this word will be over here, that would have to be put over there into this gap. This was the idea how the world should be organized in the future, using psychological manipulation. And this is how life really works, by self-organization. So it's really important that pedestrians self-organize, and that shows us really a new way of how to manage the world, how to manage complex systems. So if we don't want to end in this world, a military world, then we should learn from pedestrians. Thank you very much.